Hey students, let's go over exam number 2. And again, like all of our exams, this will give you a chance to learn from your mistakes and also a chance to self-grade. So let me start with number 1 here. It says the Golden Gate Bridge in San Francisco is 2,737 meters long. It's made out of steel. The expansion coefficient for steel is about 11 times 10 to the minus 6 inverse degrees Celsius. And that's notice the units here, because when it says here in A, how much longer will the bridge grow between a cold winter's night and a hot summer's day? Okay, so there is a change in its length, and of course we learned that to be the change in length is the coefficient of expansion, this alpha, times the original length times the delta t. And so let's focus on that delta T for a moment. You might remember that the temperature on the Fahrenheit scale is, if you want to do a conversion, the temperature on the Celsius scale. You multiply by 9/5, and then it's offset by 32. Now, in our case, we want to go the other way around. So if you take the temperature on the Fahrenheit and move this over, so subtract 32, then multiply by 5/9, you will get the temperature on the Celsius scale. So grabbing then I'll call it T1 and T2, the hot temperature, which is 88 degrees Fahrenheit, and subtract the 32 and multiply it by 5/9, gives a high temperature of about 31.1. And the low temperature of about 35, subtract 32, is 3 degrees Celsius, so that's 3 degrees above freezing, times the smaller number, 5/9, is about a 1.67. Maybe I'll put another 1 there. And so what's going to be relevant here is the change in temperature. So let me come over here and take the 31.1 and subtract the last answer. And it is about 29.4 degrees Celsius is how much it warms up. All right. So then when we come here to see how much bigger it gets, this is the 11 times 10 to the minus 6 for every degree Celsius. And it also technically means for every meters. So that's why we multiply by how many meters we have, which is 2,737. And then the increase in temperature, degrees Celsius, meters. And we're going to end up with something in meters. So taking the 29 and multiplying it by the 2,737 and multiplying that by 11 times 10 to the negative 6 gives me almost a meter, about 89% of a meter. And so 88.6 centimeters is how much it grows. And of course, this was part of our conversation, and one of the engineering challenges is, making sure that you build a bridge in such a way that it can accommodate that. And that's why, as we talked about, you would anchor one side of the bridge, which would be the San Francisco side, and then the northern side, which would be San Rafael up there, and then the bridge can expand back and forth and actually not anchor, but kind of slide, and it looks like it would need about a meter. You might even design it in case it gets even more extreme than that, so it can expand up. And so if you enter the Golden Gate from that side, you feel it right away. You kind of drive along and you hear that little thump thump, and you kind of feel that where it's not really mounted to the ground. You hear it thump as you hit the ground, and you kind of angle up with the arc as bridge is kind of built something like this. So here's the anchored side, and then the bridge goes across. Actually, that's probably not a good place to put it because it's anchored, and then it's got the two towers here. But then the deck landing on the San Rafael side kind of just lays down, and it can slide back and forth a meter. So that's all of our bridges at, and we looked at some pictures. Anyways, I digress. Let's get back to the test here. All right, so number 2 has to do with the volume. And so here it says the bridge is again made out of steel. It's actually Bethlehem steel, which has this density. What is the density when it warms up? And so since density is mass over volume, as the steel expands, of course, the significant expansion is its length, because that's where you're building the bridge for the road. But the I-beams would grow this way, which really we wouldn't care too much about, and they also would grow in their thickness also. But when it comes to density, we'll take all 3 of those here. You might even do this, put a little sub C for cold and maybe a sub H for hot, because the density is going to be different when it's hot because its volume is now different. What is same is the mass, and so that's going to be the key. You can set the 2 masses equal to each other, and so you get the density times the volume when it is cold equaling the density when it is hot times the volume when it is hot. And we're given the density when it's cold. That's the 8,050 kilograms per cubic meter. And we don't really have the volume of all the steel. We only have the length, but we don't know the size of the I-beams and all the pieces that are cut out. But that's fine, because on the other side here, we would have an equation for the new volume that looks something like this. It would be the volume when it's cold plus the change in volume. And the volume change is that beta, that's the volume growth, times the original volume times delta T. And now you can see that you can factor out the original volume when it's cold, and that will cancel off with this other side of the equation. And so we'll get the density when it's hot by taking our 8,050 and divide it by this factor, which is 1 plus. And volume expansion is 3 times the linear expansion. And so this is 3 times 11 times 10 to the minus, that was 6, right? Yeah. And the change in temperature we did earlier, 29.4. And so there is going to be our answer. What is the density? So grabbing my calculator here, I'll do this denominator first. Let's go 3 times 11 times 10 to the negative 6 times 29.4. I'll hit enter and add 1 to it. So that's the denominator. So if I take my 8,050 and divide it by that last answer, I get 8,042 kilograms per cubic meter. So density goes down a little bit. Makes sense, because the volume got bigger, and it got bigger because it warmed up. Yay! All right, so hope the first one went well for you. That's our first set of calculations. Let's move on to the second one. And you probably already noticed, but I'll say it. You'll notice that the second and the third one are not very long problems. They're relatively straightforward because 5 and somewhat 4 are pretty long ones. So let's read this one. Here we have 1 liter, so a 10 by 10 cube of ice at 0 degrees is inside of an 8 liter strong And so fixed volume container with 5 moles of nitrogen gas. So you might look at it something like this. I got a kind of a big block of ice with a bunch of nitrogen molecules floating around. The volume taken up by the nitrogen must be the 7 liters because this is taking up 1 liter. And how much of it melts? Oh, I forgot to say that the ice is at 0 degrees and the nitrogen is first at 100 degrees. And so we used our conservation of energy and said if you add up the Q's, the exchange of heat, you're going to get 0. It kind of makes sense because one's going to lose it, one's going to gain it. In this case, we are going to have energy flowing into the ice. And so that will melt the ice. And here's how we calculate how you melt ice. It is the mass that melts times the latent heat of fusion. And that's going to be a positive number because energy goes into the ice. Now it comes out of the nitrogen. And so that's going to be N, and we'll do the CV. And keep in mind that how you calculate heat for a gas would depend on what process you're doing. So we're doing a constant volume process. So it's CV. And fortunately, we can kind of put all these numbers in and just solve for M. Now, it does take a little moment to stop and think about this because you might wonder, is the cooling down of the nitrogen going to melt all the ice? And so now it turns into a liquid. And of course, it'd be a liquid at 0 degrees. So then it would start warming up. And so if it did that, then we would need another term here because not only are we melting ice, but we're warming up the ice. And our delta T would be unknown because we don't know what, the final temperature ends up at. At equilibrium, it might be, 10 degrees Celsius or something. But I tried to make it obvious that it's pretty clear because there's so much ice. There's an enormous amount of ice that this is just going to melt a fraction of it. It even is kind of implied with the question, when it says here how much melts. Again, implying that not all of it melts. In fact, you can kind of see here that if you did just some kind of quick and rough number, 5 times the specific heat, let's see, it's diatomic, so there's 5 degrees of freedom, so it'd be 5/2 times R. And if it cooled all the way down to 100 degrees, we're looking at only a little over 10,000 joules have to leave the nitrogen gas to get it all the way down to 0. But yet to melt all the ice, all the ice would be 1,000 grams, because we got 1 liter. And there is 335 joules for every gram that melts. And so to melt all that ice would take 335,000 joules of energy. And that's just way, way, way bigger than that. So for all of these reasons, hopefully you bothered to kind of check and think about it. I'm going to safely conclude right here that not all of the ice melts. And therefore, I don't need another term here for the warming up of the melted water. And likewise, I know the change in temperature is 100 degrees because we still have ice around. And so this is going to cool all the way down to 0 degrees. And so if I put in these numbers, and I'll say it again, this is the molar specific heat at constant volume, which is our 5 degrees of freedom. And by the time you put in all of these, and set that equal to 0. Oh, let me be careful. That'd be a negative 100. The change in temperature is a decrease. We can get the amount of mass. And I guess this number we already did. It's right here, but maybe I'll just do it again with the negative. So it's 5 times 5 halves times r times a negative 100. Then when you move it to the other side, it becomes positive. Then when you divide it by the 335, you get 31 grams. So 31.0 grams of ice. Again, a very small fraction, which, again, if you just kind of assumed a small one and went through, if you came up with a mass that was much less than one kilogram or 1,000 grams, you go, okay, yes, not all of it melts. And that's kind of what, if you studied the pretest material, you'll see that my colleague Don, that's how he suggests, just make a guess if all of it does or doesn't one, whichever is an easier calculation. So this is the easier calculation. And then if you come up with an answer that makes sense, then that's what happens if you come up with a number. And in this case, what wouldn't make sense is a mass that's greater than 1,000 grams. Then what you know is all of it melted and started warming up. And so you'd have to go back and redid it. And so that's not a bad technique. But again, I tried to make this one so obvious that it would be short and sweet. Anyway, so that's all there is to number 2 here. Okay. So number 2 is done. Let's go on to number 3. Number 3 is kind of like a part B. And like I said, if I almost put it as a part B. In fact, I first wrote it as a part B, but I go, nah, I'm going to make the test a little too long. So divided that into 2 easy ones to make 5 a little bit longer. But it says, what is the total change of entropy back in problem number 2? So there'd be a change of entropy of the H2O, and there would be a change of entropy of the nitrogen gas. And in both cases, and in all cases, the change in entropy is, solving this integration. So in the case of the melting ice, remember the Q equals to mdV. Then the small amount of heat would be a small amount of melted ice, LV. And so we can write this as LFdm over T. And then also, fortunately, while ice is melting, the temperature remains constant. And so that makes the integral easier to do than, say, this one. Because then this just becomes LFm over T, or maybe you could just say it's Q over T. And so this is the equation we always get to calculate the entropy if, this is a key, if the temperature doesn't change. And that's why it wouldn't work for the nitrogen, but it will work just great here for the melting of the ice. So if I take the amount of heat, the Q, and that's what this line was, the 10,387.5, that's the Q. And if I divide by temperature in Kelvin, and melting ice, remember, is either 0 degrees Celsius, but I want Kelvin, so that's 273 Kelvin. I get 38.0 joule over Kelvin for the change of entropy then of the little ice crystals. Now, you might also remember that on a microscopic level, we called entropy a measure of its randomness, its disorderedness. And so if you imagine a frozen water piece, they're all locked into an array here, a crystal grid. It'd be kind of hexagonal in their pattern if you looked under it under a microscope. Okay, so knowing that the ice is well organized, and when it melts, you just have this random bumping of H2O molecules. There's no real structure, so we'd say it's more disorganized, and that means that's this. It's got more entropy. And apparently this is the numerical value we would label it. It has more by 38.0, and the units for entropy would be Joule Kelvin. Okay. Now, doing that same logic for the nitrogen gas, but of course remembering Q equals to NCV delta T, or microscopically, a little bit of energy would be NCV dt. This then would be the integral we have to solve to calculate the entropy of our nitrogen gas, okay? And the number of moles and the molar specific heat at constant volume are a constant, so I'll pull those out in front. And now I have an integral that, comes out a little different than up here. Here we had a constant temperature, so it came out different, but here we get a natural log. And if I then put in final and initial temperatures, so here's initial, here's final temperature as my limit, and then use the property of logarithms where you subtract two logs, you can write it as a quotient. This would be then the formula for the nitrogen. And as we talked about, on a microscopic level, it's that disorganizing. And so at first it's really hot, meaning the molecules are bouncing around with a big randomness and speed. And so once it cools down, they're still bouncing around because it's not absolute zero. But there's less randomness to it because the higher speed is something less, or the RMS value is something less. So it doesn't have as many different speeds going on inside. So we would say this is more organized. So I'm expecting this to be a decrease in entropy. It's more organized. So let's see what we get. Let's see, the number of moles, back to problem 2, they said 5 moles, so there's my 5 moles. And then the molar specific heat is that 5 over 2R. And maybe I should be careful here with my units. The 5 is 5 moles. The R is joule over a mole over a Kelvin. Because then when I go natural log and it cools down to 273 Kelvin, as we talked about earlier, but it started at 337 Kelvin. That's that 100 degrees Celsius they talked about in the last problem. And so we're taking the log of something less than 1, so that's going to be negative. So that's why all this will come out to be negative. And I guess technically this would be Kelvin over Kelvin. So Kelvin over Kelvin will cancel off, and then we'll just have a number here. And then mole and mole will cancel off. And so we'll be left with the appropriate units, joule per Kelvin, for the entropy. And the appropriate sign will be negative because of the log function. All right, so if I go to solve this, 5 times 5/2 times R times natural log 273, 373. And so there's the negative, and it looks like 32.4. 32.4. So now if we want to do the total of them, we need to put them together. So here is the nitrogen. Let's come back up here. Uh, 38. I thought it was in here somewhere. Yeah, there it is right there, 38. Okay. And so we've got a positive 38 and a negative 32. We put those together, and well, 32.4. So it's not quite a 6, just shy of 6. So it looks like about a 5.6 joule Kelvin. And notice it's positive. That's our second law of thermodynamics that says, hey, when we consider all the entropies, some, in this case, as they exchange energy, the one that gains the thermal energy is going to grow in entropy, so that's the ice. And the one that loses thermal energy, nitrogen, that's going to decrease in entropy. But you'll always have a bigger gain than a loss in entropy. And that's the requirement of the second law of thermodynamics. And so anything that comes out positive like this, can happen, and it does happen. So if you put your ice together, your nitrogen, it can cool down the nitrogen as it melts the ice. And that's pretty obvious. We know that. And so I'm not surprised that the calculations tell me it can happen. The other way around wouldn't work. If we said that the ice got colder and the nitrogen got warmer, if we calculated the change in temperature, it'd be a negative. And we'd say, well, that can't happen. Even if they exchange the same energy. So you would say, well, according to conservation of energy, this, ice, which is already cold, gave up 10 joules, so now it's just colder. And the nitrogen that's already hot gained the 10 joules, so it just gets hotter. You're like, oh, that's okay. That doesn't violate conservation of energy. It's still just a transfer of 10. One lost 10, one gained 10. But the change of entropy would be negative, and that would be, the second piece of this that would say, no, it's not possible. All right, well, hope that one went well for you. Well, let's get to the longer ones on this exam. Here's number 4. Maybe I'll even grab my red pen here. Because when I ever start these problems, and if you kind of watched my videos, I kind of always like to say, okay, since a lot of these are like constant pressure, constant volume, I mean, there's things that don't change, and it's kind of nice to kind of mark those to make it easy. And that's what it says here. It says a monatomic, so we'll come back to that, gas, is compressed at constant temperature from A to T. So from A to T, we have a constant temperature. So that means right here, and I like to kind of mark it and say, hey, the temperature at A and the temperature at T are going to be the same. And in fact, since I know one of them, I might as well immediately write down the temperature of the other one. Okay. Let's see. The gas is then warmed at constant volume from T to O. So the vertical line represents a constant volume. But again, I'll just kind of make a little chain here and say, okay, those two are connected together. And again, since we know one of them, we can find the other. Okay. So it's then warmed at constant volume from T to O. Third, the gas is then expanded under constant pressure from O to M. So the horizontal straight line is O to M, and constant pressure, O to M, would mean these two numbers have to be the same. And again, might as well write that one in. And so these are the ones that I would chain together, a constant temperature, a constant volume, and a constant pressure. And then finally, the gas is expanded adiabatically from M back to A, and so that's our steeper curve. So A to T is really a hyperbola, and this is a power function, so it's a little steeper than that one. And the thing about adiabatics is nothing stays the same. The pressure changes, the temperature changes, and also the volume changes. And so we can't really put a little chain in there that would connect M to A. It's just not in there. And it's kind of hard to draw anyways because they're on the top and bottom of the little chart. But remember, this chart's really a cycle. So it goes, atom, atom, atom. And it's a cycle that can keep repeating. All right, but that's I think the best place to get started, and I hope you did that. I hope as you read it and kind of understand what's going on. You fill in some numbers by chaining them together. And then, of course, the question says, go ahead and fill out all the missing parameters. Now, the big one, the go-to one, is always to remember that PV equals to nRT. And there's 4 parameters in here, and so we have to know 3 of the 4. Usually the one that we know is the number of moles, and then we say, if you know any 2, you can find the third. And you watch my videos, you probably have heard me say that. But this problem does not give us the number of moles. So I'm going to say it as, look, if I know any 3 of these 4, and since the number of moles is the same in all of them, maybe I'll put it over here. What is N? And we're not told what it is. And we only have 2 of all these other ones. And so technically, as I look at this, I feel kind of stuck, where I know 2 of the 4, but I can't calculate the other ones. Although, this is where that adiabatic has its advantages. Remember, the adiabatic does not have any of them unchanged, but it does have them locked together. For example, pressure volume to a gamma equals pressure volume to a gamma. And so if we put M and A here, this is then saying if you know pressure and volume and pressure and volume, so if you know 3 of these 4, you can find the missing one. Well, we don't. But another way of writing this same thing is to put in place of pressure nRT over volume and do it on both sides, and you get this. You get temperature times volume, gamma minus 1, is the same as temperature times volume, gamma minus 1. And so that means temperature at M, volume at M, temperature at A, and volume at A, raised to a power of gamma minus 1, are the same. And if you look at that, here's A, we do know volume temperature. And for M, we don't know volume, but we know temperature. So looking at these 4, we know 3 of those 4. And that means we can solve right here for the volume at M. And so let me give that a try. What is my, volume at M? So I'll put in the temperature at M, which is listed there at 450. The volume at M I'd like to find. I do need to get gamma, and remember it says monoatomic. So gamma is Cp over Cv. And remember, I always like to talk about Cv. Cv is the number of degrees of freedom. So there's only 3 degrees of freedom for a monoatomic gas. Monatomic. And then Cp is 1 R above that. So if I add an R to it, I get 5 over. And so this is 5/3. So that means up here, when I go gamma minus 1, that's 5/3 minus 1, which I can think of that as 3/3. So I'll be left with 2/3 is what the volume is raised to. And the temperature at A is 300, and the volume is 20, and also raised to a power of 2/3. And if you watch my videos, I kind of always like to pause and leave the volume raised to whatever power so I can do that kind of separate. But if I take my calculator and go 300 times 20 raised to a power of 2/3, then divided by 450, I get 4.912. And then finally, to get volume raised to a power of 1, I can raise both sides to a power of 3/2. That would undo this 2/3. And so let me raise this to a power of 3/2, and it looks like 10.9. And so 10.9 liters would go right there. And that might be the key step, because remember what we said earlier is what was holding us up from doing these calculations was not knowing n. And then once we know these three, we can actually get n. And so the next best calculation here that's going to make everything open up and be easy to do is to calculate how many moles do I have. So my pressure is 686, and I guess I have a decision to make. Usually I like to do pascals, so I need to multiply that by 1,000. But I also like to do volume in cubic meters, which means I've got to divide that by 1,000. And it seems like a waste of time to first multiply pressure by 1,000 and divide by volume by 1,000 if I'm just going to put them together. So let me not, this time, multiply pressure by 1,000, and let me not divide the volume by 1,000. Because if I did, I'd get that same number. Now if I divide it by R and also divided by the temperature of M, which is 450, I will get how many moles. And it looks like to three significant figures, I have 2 moles. Nice. Now, of course, once I have that, I should be able to finish the pressure by saying it's nRT over V. And so I'll do this A, because my N would be 2, my R would be 8.31, my temperature would be 300, and my volume, if done in liters, is going to give me a pressure in kilopascals. So that's 249.3. And we can redo the same calculation, or we could notice here that what's going to change in this next calculation is not N, not R, and not T, but V. And it's going to be half as much. And so that's going to make the pressure twice as much. So why don't I just double it? And so that's going to be 490, I'll go 98.6. So there's my pressure. And then the last one here is this temperature at O, and again, you can write it this way, that pressure times volume divided by nR will give you the temperature. And so maybe I'll do the same thing, 686, and not multiply it by 1,000. Then I'll multiply by liters instead of cubic meters, so I will not divide by a volume. So there's my pressure times volume. Then when I divide by the number of moles and also divide by N, I get about 413. Yay! And so there's the full chart. And so you can see really kind of the key is to recognizing well, first of all, the ones that are the same. That's pretty obvious. But somewhere in here, there's this adiabatic, which once you get adiabatic, you get enough information in one row to figure out how many moles. And once you do that, you got all the information for the rest of them. That kind of summarizes what you would do for step number 4. All right, then finally the last one. And to try to make it a little easier on you, I tried to say this is the same cycles as the last problem, or same cycle. And so this is isothermal, isovolumetric, isobaric, and adiabatic. Okay, I labeled the points different, so hopefully you wouldn't confuse the numbers in 4 with 5. Also gave you some beginning numbers to work with, which, as it says here, you could fill all of these in, not necessary. these 6 are enough to do the energy stuff. And so let me do that. I won't bother to mess with the table part here. Perhaps not only are the numbers different, like a different number of moles. Here's a big one, is it's diatomic. But we still have all 3 cycles. So jumping down here to the energy table, if you are following any of my suggestions, I say fill in zeros where you know. For example, when is delta E equal to 0? Well, delta E is not only a state function, state function, so that must be 0. All of them together must come back to where it starts. Okay. But as a state function, then it's connected to just the kinetic motion, that is the temperature. And so if the temperature doesn't change, so that's isothermic, that would be a 0. So the H to the E would be a 0, and the full cycle would be 0. When is work equal to 0? Well, work is not a state function, so even though we do one cycle doesn't mean we're going to get back where we started, so that's not necessarily 0. It's the area under the curve, and so E to A has no area under it. Or maybe a better way of saying it's work is force times distance, and for constant volume there is no distance, there is no movement, so no work is done for the isovolumetric. When is Q equals to 0? Well, that was the definition of our adiabatic, which is this T to an H. We also, of course, said it was not a state function in any way. So that, I don't expect that to be 0. Now, the entropy, as we did in an earlier problem, is summing up all the microscopic amount of energies divided by that temperature. And in the case of the adiabatic process, you don't have any exchange in thermal energy. So the entropy there should be 0. And for that matter, entropy is also another one of our state functions. So these two are a state function, these are not state functions. So whereas these, I'm going to say, hopefully they are not 0 and not 0. Although I guess it could be. This one must be 0. We get back where we started from as we do our full cycle. So that's where I would start this problem, is put in the zeros that I do know. That's going to confuse me. Let me scratch that off. All right. So I'll put in the zeros. Then, personally, like I said, I like to do the state functions. And here's we said, if you were following mine, the best thing to do is to know that this is how you calculate the thermal energy for constant volume, and E to A is constant volume, and these two add up together to give you the E. That's how we derive this equation. But we also said, since it's a state function, you could use it for all of these. And so let me go ahead and do that. The number of moles is 4.25. And since it is diatomic, it has 5 degrees of freedom. That sounds familiar. Did we do a 5 degrees of freedom before? Oh, yeah, here was number 2. Yeah, okay. And then there is this delta T. And that's why I was saying here that, hey, you know, the delta T's are right here. In fact, if I put all 4 of them, H to E would be a change of 0. So this time 0 is 0. So I already got that one. But the next one, E to A, would be a change of 40, because it would be 340 minus 300. And from A to T would be what, 85? And then from T back to H would be a decrease of 125. And so I'll write it more like a matrix looking thing, where these will be the same for these three calculations. I'll just have a different delta T. So let me just do this number out in front. It looks kind of like an eigenvalue. So let me take the 4.25 times 5 over 2 times 8.31. And so my, if you want to think of it as a matrix, my eigenvalue times each element here is going to then transform to this matrix. Sorry, too much mathematical words. But each of these would go in this spot. So I'm going to take that number, let's see if I can fit this on the screen here, and multiply by 40, and I will get 3,532 for here. Let me just undo by dividing by 40, and then multiplied by 85. So this one would be 7,505. And let me undo the 85 and then multiply by a negative 125. And so this is going to be a negative 11,037. Yay! Now, one thing about this is already set at 0, so I can kind of check these. I wonder if these work out right. What is 3532 plus 7505 minus 11,037? 0. Yeah. So I've got some confidence that that one's looking good. Okay. All right, now, again, if you follow along in my videos, I say first find the zeros, okay, then do the state function. And by the way, I'll hold off on the entropy, although we probably could, but we kind of learned this separately. So let me hold off on just doing this chart here, because these two add up to that one. That's the first law of thermodynamics. So if you have any two of them, you can get the third one. And so we do twice here, right? We have this one and this one. So this must be 3532 also, because that plus 0 has to add up to that, which of course would be this formula, which is the same formula we'd use for constant volume anyways. This one here means that this one needs to be a negative 11,037, because again, these two have to add up to that. We can't do this one quite yet or this one quite yet, so let's hold off on that one. We might want to ask ourselves about the sign of all of these. These would be positives if they gain temperature. And so these two gain temperature, this one does not, and this one loses temperature. Okay, so I'm happy with that. Probably the one to really check, because the one the easiest make a mistake on is the work. When you squeeze something, you're doing work on it, and that's a positive number. If it expands out, it's doing work on the environment. It's losing energy. And so T to H is an expansion. And so that coming out negative is a good sign. All right. Now, A to T is a constant pressure one. So maybe to approach that one, I'll just do Q equals to NCP delta T. Because this would be the 4.25, and the CP would be 7/2 R. See, the CV was 5/2 R, so we add 1 to it. And the temperature increase from A to T is that 85. And so that would be this number right here. 4.25 times 7/2 times R times 85. So this would be 10,507. Okay. And then that opens up the fact that these two have to add up to that 1. And so if I take the 7,505 and subtract my last answer as I move it to the other side, this is a negative 3002. And again, I might ask myself about the negative, but from A to T, it's getting bigger. And so that means it's doing work on the environment. It's losing energy due to work. That's why the total increase is only 7,000. You see, you put in, here's positive, 10,500 into it as heat. But as you're putting it in, it expands, and so 3,000 comes out. This is the leaky bucket analogy that I used in class. So you end up with only an increase of 7,000 because as you put it in, some was leaking out. Okay, now maybe the harder of all of these is right here. Oh, by the way, I guess we could get this by it's constant pressure. So P delta V would be this one. And A to T. Oh, well, we don't have delta V, A to T. So we could get it, though. But with focusing on temperatures, this is the way to go, because that's what's given. Now, the reason these volumes are given will be obvious right here, because maybe I need just a little more space. Let's see, this is one set of calculations, this is another. But when I go to do, say, a calculation for work, it's the integral of negative P dV. And if we replace P with nRT over V, and say focus on constant temperature, so that's what this is, H to E is constant temperature, then I get nRT, and I can pull the T in front of the integral because it's a constant. And then I just get the integral of dV over V, which is the natural log. And then that would be final volume over initial. And that's why the volume here is listed for this one. I can get this work. So let me put those numbers into my calculator. Negative 4.25. So there's the negative, there's the number of moles, there's the R. The constant temperature is the 300. And then the natural log would be the final volume, which is 4 divided by 12. And as long as they're the same units, they cancel off. So if I have it in liters, I'll just go liters over liters. I could switch it to cubic meters or cubic centimeters. But as long as they're both the same, they're going to cancel off. And if I hit enter, I get notice a positive 11,640. Let's talk about that. Of course, the comes out to be positive mathematically here, because we have a negative out in front, but we also have then a log of a ratio that is smaller than 1. And so the log of something smaller than 1 is a negative. So we got a negative, and a negative makes a positive. And remember, work positive means that we should be shrinking it. We should be compressing it. And that's what's happening from H to E. So from H to E, we compress it. So this one should be negative. Compressed. So this one should be positive. E to A, well, that doesn't change its volume at all, so that should be 0. And these other two, A to T and T to H, they get bigger, so those two should be negative. Nice. And that might be the hardest one to get here in problem number 5. But now that we have it, we know that these two have to add up to that one. So this must be a negative 11,640. So that this plus this is 0. And we can kind of check this, because as we look at this, we go around in a clockwise direction, and that should be a net work done on the environment. So this one should come out to be negative, and that would have got a number from a heat it put in. So this one should be positive, and this one should be negative overall when we do the total. And more than that, they should be the same, because remember, these two have to add up to the 0, and the 0, we already said, is a state function. That's the whole idea of building our heat engines, is to put in a positive amount of heat and get a net work out of it. So there's our negative. So if we kind of test this, we can go 11,640. We could subtract off 3,002, and we could subtract off 11,037, and we get a negative good, 2,399. Then I hope this comes out to be a positive 2,399. Let's see, just to kind of check, negative 11,640 plus 3,532 plus 10,507. Yep, and there it is, positive 2,309. Okay, good. Well, getting close to wrapping this up. Like I said, this number 5 is a long one. Let's jump over here to our entropy calculations. Now, maybe to do that, I'm going to grab a scratch piece of paper. Actually, maybe I'll just do the back here of number 4. All right. But as we mentioned earlier, our change of entropy is always calculated by completing this integral. And now we'll have all 4 cases. The easiest case we've already done, right? The adiabatic. And so if I kind of write this again as a matrix, I'm going to put then 0 for this adiabatic one. Because another fairly easy one to do is, what if the temperature is a constant? If it's constant, you can bring it in front of the integral. You got the integral of just dq, and so you just get a q over a t. And that would be the formula for the isothermal. Now, for the other two, they are either constant volume or constant pressure. So you are going to get something like this, where the number of moles and then the molar specific heat, either constant volume or constant pressure, gets pulled out in front, and then you just have a log of final temperature over initial when you do the integral. And so this one here would be NCV, natural log of final over initial. And this would be NCP, natural log of final over initial. And so those are our sets of formulas. And so let me do the first one. We have this Q at a negative 11846. And if I divide it by its temperature of 300, this is a decrease of 38.8. And again, hopefully that makes sense because we are decreasing the complexity of it. We're decreasing the disorganizing of it. I mean, as we squeezed it, we actually gave it less space. That's really the main reason. We haven't changed their velocities in any way because this is constant temperature. So you could argue that all of this is now more organized, not because they've slowed down at all. They still have a lot of random different speeds to them. They're still at 300 degrees, but it's more organized because we have now created it in that same motion in a smaller volume. So that's a decrease in entropy. Whereas the E to A would look something like this. It'd be the number of moles, 4.25, times CV, so that's 5 over 2 times R, times the natural log, and let's see, it's going to be 340 over 300. And so we get a positive 11. Maybe I'll round it to 11.1. But again, notice the positive number there. That means it is more disorganized. And that's really what's happening from E to A. We've kept it in its same volume because we're warming it at constant volume. But now we're making them go faster. And so there's a bigger distribution, a bigger randomness to their speeds. And apparently it calculates out to be an increase of disorganization by about an 11, so a positive there. All right, now from A to T, again, I guess I'm expecting another positive number because as I go from A to T, I'm actually increasing the temperature quite a bit. So there's more disorganizing because of their motion. But in addition to that, I'm increasing its volume, and that would be a more disorganization. So this is going to have quite a bit of disorganization because as it goes from A to T, they have more space and they have more speed. And so they have a more crazy randomness to their speed and also spread out over a different area. But the calculation is hopefully pretty straightforward. Let me plug that in. 4.25 times CP. Now remember, CV is 5 degrees of freedom. So this would be 7 halves times R. And then times the natural log of, and let's see, this would be final temperature of 425 and initial temperature of 340. And so this would be a positive 27.6. And as we mentioned earlier, these should add up to 0. Because we get back, ultimately we get back to H. When we get back to H, we're going to be at the same temperature, so they have the same distribution in terms of their random movement, but they're also at the same volume, so they have the same disorganization in terms of their volume. And sure enough, that's looking really good. If I go negative 38.8, add to it 11.1, add to that 27.6, I get something that can be justified as a small rounding error as a negative 0.1. And so other than rounding, it's perfect. Okay, so there completes our table. And technically, we got another little step here, so let's not forget it. B is the efficiency. I guess there's a couple ways we could do that. Maybe I'll use the other side here and look at my chart with you. But in terms of efficiency, we could take the net work that is being done, absolute value, and divide it by the thermal energy added in. We also said that you could write that as 1 minus the energy that comes out of it, the thermal energy, divided by the thermal energy that goes in. Maybe we'll do both to kind of double check. This one kind of seems the most direct, straightforward process because I see that the work at absolute value is 2,399. Maybe the harder one is to make sure I only include the thermal energy that's going in. So that's positive numbers. And so these two positive ones would be put together, not the stuff coming out. The stuff coming out is this cold one. And so I'm going to add those two together, the 3532 and the 10,507. And we're looking at about 17.1% efficient. And that should hopefully come out to be the same thing here. If I take the absolute value of the energy coming out, that's the 11,640, and divide it by the energies going in, 3532 plus 10,507. And then I go 1 minus that last answer. Oh, good, I get 17.1 again. So 17.1%. And of course, any real cycle, this is not needed, but the best efficiency we could do would be based on the formula we got during a Carnot cycle. Now, this is not a Carnot cycle. So we would expect this efficiency to be less than this number. And so our coldest temperature is 300. Our highest is 425. So if we go 1 minus this last answer, based on these temperatures, best we could ever do is 29.4. That would have been a good question to ask too. But I didn't. And so you just have to put the 17.1. All right, well, say it again. Hopefully that was a good test for you. You can see number 5 was pretty long. Hopefully you did well. Hopefully you caught your mistakes. As your education continues, you won't make those mistakes again. And hopefully you'll feel a little comfortable about what your score is, and I'll start grading these and get them back to you by next class time here. But I'll need a few days with grading everybody's. All right, take care, everyone.